Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. A big thanks to everyone who joined us last week for our second TWIML online meetup. Led by Nikola Kucherova, we discussed the paper Learning Long-Term Dependencies with Gradient Descent is Difficult by Yoshua Bengio and Company. I had a great time and learned a ton. For those who weren't able to attend live, we have the video posted for you on twimlai.com/meetup. And if you're interested in joining us next month, please head on over to that site to get signed up. We're also accepting presenters, so feel free to shoot me a note with your ideas. Next up, the time has come for the Artificial Intelligence Conference, brought to you by O'Reilly and Intel Nirvana. I'll be in San Francisco the entire week next week, and we have a ton of great interviews lined up. So this should be another awesome series. If you haven't had a chance to check out our series from the New York event, you can find it at twimlai.com/O'ReillyAINY. Also, if you'll be at the conference, please send me a shout out on Twitter or via email. I'd love to connect. See you then. Okay, about our show. This week, I'm bringing you an interview with Bruno Goncalves, a Moore-Sloan Data Science Fellow at NYU. As you'll hear in the interview, Bruno is a longtime listener of the podcast. We were able to connect at the NYAI conference back in June after I noted on a previous show that I was interested in learning more about Word2Vec. Bruno graciously agreed to come on the show and walk us through an overview of word embeddings, Word2Vec, and a bunch of related ideas. He provided a great overview of not only Word2Vec, but related natural language processing concepts such as skipgram, contiguous bag of words, Node2Vec, TFIDF, and much more. By the time you hear this, it'll be too late to catch it live, but Bruno is doing a half-day tutorial on Word2Vec and Friends on Monday at the AI conference. If you'd like to see it, I'm sure it'll be available via the O'Reilly Safari website. And now, on to the show. All right, everyone. So I am here on location at the O'Reilly AI conference, and I have the pleasure of being here with Bruno Goncalves, who is apparently a longtime listener of the podcast and reached out to me after hearing me note that I wanted to learn more about Word2Vec and embeddings and made it happen. So we're here to talk about that. Welcome, Bruno.
Thank you. It's a pleasure to be here. So I've been listening for a very long time, and I'm very happy to be here and be able to participate.
Awesome. I was just asking you, you mentioned that you've been listening since before the interview format. And I don't know, I'm still stuck on like the transition from the news format to the interview format. How was that for you? Like, what's your take on kind of the before and after?
No, I like the new interview format, actually. But this might be a personal bias. When it was news, a lot of the news I'd already seen or listened somewhere else. Mm-hmm. So it wasn't as new. And this way, since you're interviewing people that I don't necessarily listen to and I don't know personally, so it's good to have a fresh view from them.
That's great. Like I said, I was, I guess I still am hung up on the fact that I switched the format, but I've been told by people that things along the same lines, that the news is essentially commoditized and it's hard to, beat out TechCrunch or whatever that people count on for their news. But the folks really seem to be enjoying the interview format. And so, again, it's great to have you on for an interview instead of talking about the news. So tell us a little bit about kind of your background and what you're up to.
So I'm originally a physicist, but I've always been involved in optimization problems, originally in spin glasses. Optimization and data mining.
Spin glasses?
Spin glasses. So it actually has interesting connections with neural networks and how they work, but it's basically a disordered magnetic system. So to put it very, very simply. But the mathematical structure is very rich, and it leads itself to exploring different types of optimization problems. But from there, I evolved very quickly, and this was because I noticed that in spin glasses, a lot of the behavior you see has to do with the way that the different elements are connected. I moved very quickly towards networks and studying basically connections between components of a system.
Okay.
More deeply. And when you're working with network and complex networks in general, what you do a lot is basically data mining. You're crawling websites, you're parsing Apache logs to look for connections between URLs, for example. You're basically doing, in a sense, applied graph theory, but applied to real data. So the transition towards data came very early and very naturally, even before, people were talking about data science. This was back in maybe 2006, 2007.
Okay.
And then more recently, I've been moving more towards more data science intensive aspects, and hence my interest in Word2Vec and that type of algorithms.
Okay. I think the best way to do this is to just jump in and have you kind of walk us through Word2Vec, but the kind of the foundational thinking that led to Word2Vec and embeddings. As I mentioned the other day, it's an area that I've been meaning to dive into, and I'm glad you're here to tell us about it.
Excellent. So the original idea is actually, as many things do in this field, comes from outside the field. So it comes from linguistics.
Okay.
And was expressed more or less in a very general way by James Firth, if I'm not mistaken, around in 1953.
Okay.
And basically what he said is you'll know the meaning of a word by the company it keeps. So if you want to understand what the word means, you kind of look at the context, and the context gives clues about what the word says, right?
Okay.
What it intends to say. So Word2Vec tries to take advantage of this by saying that the embedding of a word is defined by the context in which it appears. So words that appear in the same context are more somewhat equivalent. So they will have vectors that are close to each other, while words that tend to appear in very different contexts will be very different and have very different vectors, or vector representations in this case.
And so how do you get to the word vectors? I guess my impression is that it's all relative to a specific corpus, right? There's not like we haven't done Word2Vec on everything, like some grand unification of Word2Vec. Is that the right way to think about it? And then you're doing some math on that corpus to get you to the vectors. Can you talk a little bit about that process?
Yeah. So basically what it does, it's a very simple neural network. So it just has one hidden layer. The activation function is linear, so it just passes through. So it's very simple. What the actual word embeddings are basically the weight on this hidden layer. Depending on which model, it can be skip grammar, it can be continuous bag of words. It can be the weight on the leading to the hidden layer, it can be the weights outside, heading out of the hidden layer. But in practice, it's the same mathematically.
And so does skipgram refer to one of those and continuous bag of words refer to the other? Skipgram is leading in, the weights leading in. And
yes. So the way you look at what Firth was saying, that you know a word by the company it keeps, is if you have the word, you can kind of guess the context in which it appears.
Right.
Or if you have the context, you can kind of guess what word would fit in the middle. So the skipgram and the continuous bag of words basically look at these two approaches. On one case, your input is the word, and you're trying to guess in the output layer what the context is. On the other case, you have the context words as input, and you're trying to guess what is the word that might go in the middle.
Okay.
And here, just to clarify, the context is usually defined by a window of words before that word and the words after that word. So if you're looking at word I, so your context would be, for instance, I minus 1, I minus 2, and I plus 1, I plus 2. Like 2 words before, 2 words after. Or 5 words before, 5 words after.
Okay. And so that window is what's used to compute the vector for a given vector representation for a given word.
Yes. So that window will give you what is the context, and the context will define what is the word. Right?
Okay.
Now, like you were saying, people haven't done Word2Vec in all the text in the world.
Right.
So every time you run this, you will get different vectors.
Right.
Also, if you run it twice in the same corpus, the vectors will be different. The reason for this is you're initializing all the weights, all the vectors randomly.
Right.
And then you're adjusting them.
Okay.
So you will end up with something different. However, if you do it well enough and it converges and you get something that's reasonable, the vectors will be different, but they'll basically be a rotation. So you can always get vectors trained into corpuses and align them so that they match. Because what the Word2Vec algorithm and similar algorithms are trying to do is learn the relations between vectors. So you're basically, you're trying to define the differences of vectors but not the actual vectors, right? So
there's some distance metric or something.
So if you rotate, the distances all remain the same,
right?
So they're still valid.
Okay.
And it's because the distances are preserved, rather it's the distance that preserves the semantic meaning, that gives you the semantic relations, right? And the idea is very simple. So if the same word, or rather if two words appear in the same context, they have to be defined by similar vectors. And this also means that if the relation between this pair of words and the relation between this pair of words is similar, the difference between them in terms of vectors will also be similar.
Okay.
So this is why you can do word arithmetic and say the vector for Italy minus the vector for Rome has to be equal to the vector for France minus the vector for Paris.
Right.
So if you have three of these, you can calculate the other one.
Right.
And basically, this is one of the ways they use to calculate or to measure how good the embeddings are. They use this is called analogies, right? So Paris is to France, is Rome is to, and they'll give you Italy if you look for the vector that's closest to that difference.
Okay. Interesting. So one of the questions two questions come up for me. One is, if the context is defined by this narrow window, you said it's usually used 2 words before, 2 words after.
I gave the example of 2 words. In the official implementation, I think the default is set to 5, but it depends. You can vary it. It's an input parameter. And also, in practice, if you want to go into the details, when you're pre-processing the corpus, you will sometimes remove some words because they're too common, kind of like what you do with stop words.
Right.
And that effectively changes the size of the window, right? Because you do this before you calculate the context. So it's almost as if sometimes your window is a little bit bigger.
Okay.
Because you remove the word.
Right.
So you're catching more information.
Okay. So the question is, do folks experiment with bigger windows, or is it possible to do this on the entire corpus and get, I guess in my mind, what I'm hearing is the word relationships are only relative to this very small window. And wouldn't the vectors capture more information if we were somehow creating them based on bigger windows or the entire corpus? Is that the right way to think about it?
Yes and no. So if you make the window too big, you're basically including information that's not relevant for the word. Right? Because you can have a very long sentence. The word at the end of the sentence doesn't necessarily have anything to do with the word at the beginning of the sentence. Right? So you're trying to keep nearby words that help you define what that word means.
Right.
So adjectives, verbs that are directly related to what the concept is or what the word is in particular.
Right. I guess I'm thinking about it in the context of like running TFIDF on a Wikipedia article, right? If I'm looking at a Wikipedia article that's talking about neural networks and CNNs and RNNs and, artificial neural networks, all these are all related terms, and I'd want to capture that relatedness, but they may be in, very different, they may be far from one another spatially in my document, but I still want to capture that context. Can I just not use Word2Vec for that?
You can. So basically what you're doing is you're scanning through the entire document.
Right.
And the embedding that you learn for each word has to do with all the contexts it appears in. So it's not just one. So like you gave the example of artificial neural network, right? Artificial will appear next to neuron in this context. But maybe a few paragraphs later, it will appear next to intelligence or to approach, right? So that means that artificial will be defined by all of these contexts and they will look very differently than a word maybe like evolutional that always appears next to neural network and doesn't appear in other contexts.
Right.
So it does take the whole information of the corpus into account.
But if, for example, I'm running it on a Wikipedia article on neural networks, and there's one section on convolutional neural network, and then another section on RNNs, and another section on LSTMs, since those individual terms are separated by these sections, will it capture those relationships via just the neural network part, or?
Yes. So one thing, maybe I should be clear. So when I say corpus in this case, I mean all of Wikipedia. I don't mean one page of Wikipedia.
Okay.
So these are very large corpuses.
Got it.
And the reason why I use a very large corpus is because you want to learn what is the meaning of the word, in a sense. Right?
Okay.
So this is what you're trying to capture. It's not necessarily what does this word mean in this document.
Got it.
So it's a more generic thing.
Okay.
And this is why actually people have started publishing high quality embeddings Google has published some, Facebook has published, that are trained on billions of words, or rather corpora that are billions of words long, because they're trying to capture what is the exact meaning. So you can use, for instance, these vectors. One very simple application is, for example, for query disambiguation. Right? Because if you know the word, you know what the vector is, you can look around that word to see what are words that are related to that one. And maybe you can show results that use those other words.
Okay.
You can use the vectors and this translation invariance, this distance preservation, as a way of mapping the word, for instance, to a verb version of the word or a noun version of the word or a past tense version. So you can use all of these relations, in a sense, all of this linear algebra as a way of getting more knowledge about what the text is.
Okay. Interesting. So the other question I had was the length of the vector. Like, how do you know what the right dimensionality is for these vectors?
As far as I know, there is no well-defined way of measuring what is the optimal size.
Okay.
In practice, people tend to use dimensions between about 100 and 500.
Okay.
Which is relatively small.
Right.
For corpora, or rather dictionaries, so the number of individual words of the order of hundreds of thousands. So in a sense, one of the things you're also doing is you're doing very much a dimensionality reduction. Right? You're mapping this from this very large, high dimensional space, where each dimension is a word, into this very small space in a way that is still preserving the meaning of the word, the semantic value of the words.
Okay. Okay. Do you recall the show that I did with Francisco Weber?
Maybe.
He was from cortical.io, and he talked about the kind of neural representations.
Yes, I actually remember that, wanted to look into that more carefully. Because he explicitly mentioned like that this is actually correlated with this type of vector representations, because it seems that each word is actually represented in different parts of the brain at the same time. Right. So it's something I'm curious to look more deeply into it. I tried looking at their website, but I couldn't get the technical details to it.
Okay. I was curious if you had looked into that at all, and if you were familiar with that model, and any thoughts you might have on
I don't know the
how
details.
that compares to...
I found some things online, but it seemed to be more marketing oriented, so there wasn't like the scientific articles behind them.
Okay. So embeddings has been around since the 50s. Word2Vec now is did you say 1950 something?
So 1950 is the idea, is this idea that the meaning of the word is coming from the context it appears. So this is called the distributional hypothesis in linguistics.
Okay. Embeddings themselves?
Embeddings have been around for maybe 10 years, maybe a little bit more.
Okay.
In practice, or like in wide adoption. They became very popular and get a lot of attention with Word2Vec, when Word2Vec was published in 2013. By Tomasz Mikolov, if I'm not mispronouncing his name horribly.
Okay. Okay. And so, we're a few years into Word2Vec, and now there are a bunch of other TVECs, right? Have you looked into any of those as well?
Yes. So there's some that are very interesting. There's one, for instance, that is DNA2Vec, and it tries to find embeddings for sequences of DNA.
Okay.
And see how that might relate to protein structure and genome organization, which I find fascinating. There is one by Jure Leskovec in Stanford, where it's called Node2Vec, and it tries to use this
node
like
to vec? Okay.
Like in a graph, where it's basically trying to do that to find embeddings for nodes in graphs as a way of measuring relations between nodes. And basically the way it does it, since it doesn't have a sequence of words, it doesn't have a sequence of nodes. So what it does is it basically runs a random walk process on the node, and that generates the sequence. And then based on that sequence, then you can treat each node as if it was a word. It appears next to other nodes because they're somehow in the neighborhood, and from there you can define the thing. And from that is able to capture some of the structure of the network, which is kind of interesting. So the idea is
that I guess I would have thought that a graph is its own kind of representation of all this information.
It is and it isn't, in a sense, right? The point is it's not necessarily easy, and this is a well-known problem, to compare graphs, right? So I'll give you a graph and tell you the nodes here are words. And I give you another graph and I tell you the nodes here are people. So you can't just match the labels directly.
Right.
It's very hard to see if the structure of the graph is the same. Because you have to look at all the permutations, at all the things. So if I'm not mistaken, I think it's like an NP-complete problem.
Okay.
So people have been trying this idea of graph embeddings for a while, where you try to map the graph into some set of points that does not depend on the details of the graph or the labels that you give to nodes or anything like that.
Okay.
Or any permutations you do.
Interesting.
So I've been fascinated by basically how versatile this idea of Word2Vec is.
Yeah, are there others? I'm at a loss for. I know I've seen it. It seems like a dozen of these different, X2Vecs of late. But it sounds like anytime you have, a space with some complex structure, this is a tool that you can use to allow you to compare both individual points within that space to other spaces. Is that a general way to think about it?
More or less. It's more whenever you have a sequence of tokens, let's say. You can use it as a way of finding a representation of these tokens that then you can use to find the relationships in this sequence. Right? So it works very well for text because you have sequences of words. Like in the case of DNA2Vec, it works very well because you have a sequence of nucleotides in DNA. For Node2Vec, you have a sequence of nodes that generated by these random processes, these random walk processes on the graph. And they actually try different definitions of the random walk, different rules. And so that's somehow able to capture different aspects of the nodes of the network structure.
Interesting. And do the sequences have to have, I guess the relationships between the tokens and the sequences are defined by the corpus. I guess I was thinking I wonder if you can do like transaction2Vec and like do a word to embedding on a sequence of transactions and use that for fraud detection or something like that.
I have actually saw something like this yesterday on Medium. I didn't read because I didn't have time. But there was literally, I don't remember the details. There was literally something like stock2Vec that somebody published on Medium yesterday. It's on my reading list, but I have not read it yet.
Oh, interesting.
So I don't know how they're doing it. I just saw the title.
But notionally, there's something in there somewhere.
Yes. So in principle, every time you have a sequence, you can do something like this.
Yeah, I've also been getting more into learning about blockchain and how that all works. And I'm wondering now if there are some applications to that as well.
Possibly. I have not seen anything with blockchain using this. I've looked in detail at blockchain a couple of years ago. I was interested in basically these transaction networks in a sense. It might be possible to do something. I said I haven't seen it yet. So interesting. Maybe an idea for some of your listeners.
Yeah. What are some of the most interesting, or what are some of the interesting applications you've seen of Word2Vec and friends?
I'm fascinated by basically how much power these word vectors have, right? Because they are capturing these semantic relations, means that you can use them for disambiguation, query expansion, analogies, like the original metric that they used. So basically, they're a very powerful tool to map text into a vector representation or to a numerical representation that then is very powerful in how you can manipulate it, right? Because everybody knows computers have a hard time understanding text, but they're very good at understanding vectors.
Right.
So here you're mapping text to vectors. So you're making computers' lives much easier. So people have used this for machine translation, right? Because you can translate vectors into calculate vector embeddings for two different languages. Then you align them, right? Because the relationships have to be the same, mostly. And then you can use them basically to match. So you find the word embedding in one language.
Right.
You find what is the most similar word, most similar vector in the other language, and you can find the translation.
Also an idea that came up in the Francisco Weber conversation. So yeah, we both need to dig into that more and try to figure out what they're doing that's different than regular embeddings.
I mean, and then there's other variation. There's also global vectors that tries to do a different formulation of these vectors. Another very interesting application, which is actually the reason why I started getting interested in Word2Vec in particular, is this paper I saw, which is actually tracking linguistic change over time. So they train, using Word2Vec, they train word vectors using Google Book Ngrams data for different decades.
Okay.
And then they align the vectors, and then they look for the words that are changing over time.
Oh, that's interesting.
So you can track basically how the meaning of a word is evolving.
Is there a metric for measuring the, I guess, like dispersion of the vectors in a given embedding? Like I'm wondering if in that example where you train an embedding on this Ngram data, can you look at, something analogous to like the standard deviation of the words or like the spread of the degree to which
Not really, I don't think. No. I mean, if you look at the entire set of vectors by itself, I don't think so. Because what you're doing is you're starting with a bunch of random vectors, then you're slightly adjusting them, so that specific pairs have specific relations between them, right? And that specific groups have specific relations between them, so they're more or less at the same distance from each other, etc. But all of these groups and all of these words can be arbitrarily rotated with respect to each other.
Okay.
So I suspect that if you just get even very high quality embeddings,
right,
and you just start measuring distances between them, it will look random.
Okay.
Because you're putting in too much noise, right? The distance between, I don't know, bed and blue doesn't necessarily mean anything.
Immaterial, right? But then more generally, there's not a set of statistics or metrics or things that are relevant at the aggregate level for the embedding?
Not that I know of, no.
Okay.
Usually what people do is they look for specific relations between specific words. So they do this analogy problem.
Yeah. Yeah. Okay.
Because that's kind of how you check that what you're capturing is what you think it is. Right? You're actually capturing the semantic meaning of the words and the semantic relations between words.
Why do we end up using neural nets to do embeddings? It seems like pretty basic math that you can do like more deterministically.
Yes. So I think that's one of the motivations for people to invest in GloVe, and GloVe is abbreviation for global vectors, and this is, I want to say it's coming from Stanford. I might be wrong. And basically they try to do it basically in a deterministic way, in an optimization defining an optimization process by specifically saying I want vectors where the relationships are given in the specific way.
Right.
The reason I think one of the motivations for using neural networks for this is because now you have very powerful tools to optimize and train neural networks in large scales. So you can use all of that machinery. Because when you actually look at the mathematics and the network structure it's actually using, it's actually very simple. So it's an extremely simple neural network.
Right.
And where it's mostly vector multiplications and then a softmax at the end with some exponentials. So it's nothing particularly sophisticated. If you look at networks like ImageNet or AlexNet or something that have dozens of layers and very complex, right? So you have all the technology that was developed for these very complex things that's being applied to something that's very simple, so it makes it very efficient.
So single layer, the matrix multiplications are just applying your weights coming in and coming out. And then remind us what softmax is.
So softmax is just an optimized way basically to calculate what is the maximum value of a vector. Right?
Okay.
And in a very simplified way, while at the same time basically turning a vector of numbers into something that's normalized. So the only thing you do is for each element of the vector, you just take the exponential of that value, and then you divide by the sum of all the exponentials. That's it. That's softmax.
Okay.
And what that means is basically makes any value that is slightly larger than the others will become much larger, so it's easier to capture the maximum value. And then, of course, there's many optimizations on top of that. That's the general idea, because you don't necessarily want to calculate all the exponentials for the entire vector, because these vectors are basically one-hot embeddings of the words in the corpus. So this can be 100,000 or 1,000,000 words. Okay. And so you don't necessarily want to have to do that at every iteration. So then there's hierarchical softmax. There's all sorts of tricks to try and optimize
more like computational tricks for...
Yes. Okay. But the concept is very simple. And then there's, of course, optimizations that people apply to it to make it more efficient and more robust.
Okay. And so what's the relationship between the one-hot encoded 10,000 dimensionality vectors and the 100 to 500 vectors?
So like I was saying before, computers have a hard time understanding text, but they're very good at understanding numbers.
Yep.
So what you do is you map, in the beginning, the first approximation is you map words to numbers. So you just have a dictionary. This is word number 1, this is word number 2.
That's your one-hot encoding.
And that's your one-hot encoding. Right. So it's just the way you represent the words so that then you can manipulate them numerically so that you can calculate these vectors.
So I'm imagining that's your very first step. Then your input layers and it's just one layer, but your inputs, you're sending in the inputs to
the hidden network
layer, and then the hidden layer one-hot encoded.
So basically,
corpus.
You have the input values here, right? And these are, let's say, in the case of skipgram, this is just the context word that you have in it. And this would be, if your dictionary is 10,000 words, this would be a one-hot encoded 10,000 dimensional vector.
Right.
This gets fed into the hidden layer in the center, which is the dimension of the embedding, which is, say, 300. And then from this hidden layer, you're trying to calculate the context. Right? And the context can be, depending on the window size, can be, let's say, 10 times the size of the dictionary.
Okay.
So it'd be 10 times 10,000, so the 100,000, right? Because you're trying to predict 10 words. 5 words before, 5 words after.
Okay. So then you've got your dimensionality 10,000 or so vector coming in. Your network is the dimensionality of your hidden vector. That's your hidden layer. And then the output side is 100,000, you were saying? It's like 10 times 10,000?
Yeah, if your window size is 5, you're trying to predict all the context from a single word. Then you're trying to go from 10,000 to 300 to 100,000.
But you're not really using the 100,000. You're just using that as kind of an optimization to get at the weights for the 300, and that's what you use?
Yes. So basically, you can think of Word2Vec actually as an unsupervised learning problem, because you're feeding it the inputs and the outputs so that you can learn something about the system. So you're not really, in practice, you're never really trying to predict the output. Right? In the set, I guess you could use that if you're trying to use it to generate text, but that would be a bit unusual.
Okay.
So you're trying to basically see what the network is learning from the text that you're giving it. And you're giving it the word and the context, and you're saying, okay, figure this out. Figure out what is the right representation that from this input can generate this output.
Okay.
And then in the end, what you're interested in is actually this internal representation, these word embeddings, these vectors.
Awesome. This has been super helpful. Like, I feel like I finally understand this now.
It's easier to explain with pictures and drawings, but
for folks that are not in the room, Bruno's like moving his hands around and like drawing, layers in the air and stuff like that.
I can send you the link to my slides if you want to actually see.
I was actually just going to ask, like, if someone wants to learn more, what's the best way for them to learn more?
I mean, all of these papers are online. You can find them easily. I'm preparing this tutorial for O'Reilly AI in San Francisco in September.
Okay.
I will post all the slides and all the code in my GitHub.
Okay.
Right now, there is already the slides for a shortened version that I presented a couple of weeks ago. Okay. So I can share that with you. And then eventually, after O'Reilly AI, I will update it with all the newest stuff.
Okay, great. Yeah, so send that over and we'll get that in the show notes.
Excellent.
And yeah, great. Thanks so much for stopping by.
Thank you for inviting me. It was a pleasure.
Awesome. All right, everyone. That's our show for today. Thank you so much for listening, and of course, for your ongoing feedback and support. For the notes for this episode, head on over to twimlai.com/talk/48. If you liked this episode or have been a listener for a while and haven't done so yet, please take a moment to jump on over to iTunes and leave us a 5-star review. We love reading these, and it lets others know that the podcast is worth tuning into. One last note, you've probably heard me mention Strange Loop, a great technical conference held each year right here in St. Louis. We're a bit over a week away from that conference, so I encourage you to check them out. It's thestrangeloop.com. I'll be there. Let me know if you'll be there too. For more info on any of these events, check out the show notes. Thanks again for listening, and catch you next time.